let's start directly with the SystemC standardization update now. The first part of the talk will give an overview of Accellera. We have a quick look at the membership list. We will talk about how to join a working group and about the global SystemC presence at various events. Then we'll have a glimpse at the success of the IEEE 1666 standard in terms of downloads and interest from the public. And then I will come to the main part of the talk, which will give an update on the activities in the various SystemC working groups. We have a bunch of members in Accellera, all contributing to the success of Accellera standards. I will not list all of them, of course, but without the contribution of the members, the work of Accellera would not be possible because it's completely volunteer-driven. Of course, you can also join a working group and contribute to the evolution of the standards as well. So if you go to the Accellera website, you find the working groups there. And there's a small link down there where you can click and register to join a working group. But also, if your company is not an Accellera member yet, you're welcome to contribute to the SystemC community, where we do have forums and an upload area for contributions and also various news. So feel free to check it out if you haven't done so. So it's a lively forum where you can find answers and have discussions on things that are in your current problem space. Okay, for SystemC in 2015 and 2016, because some of the events already happened this year and will continue to happen next year as well, we have a SystemC presence throughout the globe, starting with DVCon US, which has been earlier this year, and DEC as well in USA. And then we have the DVCon India and DVCon Europe, where we are right now. And there's, of course, also presence in Asia with the SystemC Japan event and the Accellera Day in Taiwan. As you can see, for the SystemC standards downloads, we had a huge peak after the release of the 2011 update of IEEE 1666. And since then, we have a continuous interest with steady downloads of the standard, which you can get for free, thanks to the Get IEEE program sponsored by Accellera. Okay, so let's look into the SystemC standardization as it is happening right now. I think all of you know what SystemC is and what the different parts are it is comprised of. First of all, we have, of course, the core language, which is worked on in the language working group and is standardized by IEEE under 1666. And together with that, there's the TLM working group looking at transaction level modeling, which is also part of the IEEE standard since the last update. Then we do have analog mixed signal extensions. We do have the verification working group looking at extensions to improve verification methodologies based on SystemC. We have configuration, control, and inspection. And on top of that, there's, which is not depicted here in this picture, we have the synthesis working group looking at synthesizable subset of SystemC for HLS. So that's the bigger picture. And all of the different activities are handled by separate working groups, which I will now give an update individually. Okay, for the language working group, the main topic is the core language and the extension and development to fit the needs of both the users and also other standards that are relying upon the core language. For the current status, we had a maintenance release in April last year, and we're currently collecting, addressing, and refining the proposals that are coming in incrementally towards the next IEEE update, which is scheduled for later this decade, I would say. And we're looking at extensions to the core language that might be needed by other working groups or other standardization activities. For the current plans, there's still an ongoing discussion on potentially required extensions or possible extensions towards the parallelization of SystemC simulations. And this is a challenging topic. Of course, additional contributions are needed. It's always difficult because it touches the core of the, tool domain where you have simulators that want to have a competitive advantage by providing parallelization extensions. But in order to achieve interoperability, some annotations might be needed to the models in order to achieve parallelism, and that's exactly where the standardization part kicks in. So if you're interested in this topic, feel free to contribute to the language working group on that area. The SystemC TLM working group was a bit dormant for some years after the inclusion into the IEEE standard, but now it has reconvened and is actively working on extensions towards additional protocols beyond memory mapped I/O, which we will see partly later in this tutorial. This includes simple signals at the transaction level where you might not want to use plain SystemC signals. Also serial communication, bidirectional communication, more or less everything that happens where subsystems interact but don't do so in a memory mapped manner. For the synthesis working group, the public review of the synthesizable subset version 1.4 has been completed in July this year, and the plan is to have a release as an Accellera standard by the end of this year. And afterwards, the plan is to start working on new topics for the second version of the standard. Then there's configuration, control, and inspection, or CCI, which is, again, talking about the interface between the tool world and the model world. The models are written by the users, and you have tasks like configure your models, you want to describe the state of the model, and want to extract data like performance figures or power or whatever other stats you're interested in. And you have tools given to you by the EDA vendors that provide you with additional value to access these parts. And the question is, how do we write models that work with different tools? And that's the scope of the CCI working group, defining the standardized interfaces, and it's currently focusing on the parameters to handle the configuration of the models. The current status is that there is a requirement specification, which you can download from Accellera. We have, within the working group, a proof of concept implementation for discussion and, let's say, experiments on the current standard. And during this evaluation, we have identified key improvements here, and we're currently looking at these improvements to be added both to the LRM that's under preparation and to the proof of concept implementation for validation. The idea is to have a draft standard for public review in 2016. And again, we are looking for contributors and also active participants in the working group here. On the analog mixed signal side, we now had the typical Accellera process to hand off an Accellera standard to the IEEE. So the SystemC AMS 2.0 standard, which was an Accellera standard, has now been handed over to IEEE. And the IEEE ballot in this IEEE SA, I think, has completed last week. And the idea is to have an updated user guide for next year based on this final IEEE 1666.1 standard for the AMS extensions. In the verification working group, there was an updated SCV release, which was the original SystemC verification library, but it is, from the methodology side, not necessarily the latest and greatest you want to use in system-level verification, especially when you hear a lot about UVM in all our other areas. So in 2015, the verification working group focused on the integration of the UVM methodology into SystemC natively. And after this has completed, they're planning to look into coverage APIs and further explorations for additional needs at the system level. And as this is a very interesting topic, I have an additional slide on UVM SystemC today. So UVM SystemC is a native implementation of UVM in SystemC or in C++. There's a language manual ready right now, and there's an open source proof of concept implementation, which will be in public beta later this year. And if you're happy to be a working group member, you will already have access to this, so it's another reason to join Accellera working groups. So this was my standardization update on SystemC. And of course, I did a lot of promotion to join forces to advance the standards together. So there are plenty of things you can do. You can share your experiences through the community forums. You can show your support by publicly recording your adoption. And of course, you can become an Accellera member and join the Accellera working groups.
And welcome for the joint presentation of STMicrolectronics and Bosch. So the title is What is needed on top of TLM2 for bigger system modeling. So my name is Martin Schnieringer. I'm with the Corporate Research Department of Robert Bosch. And before I continue, would like to quickly hand over to my co-presenter so he can introduce himself.
And my name is Jérôme Cornet. I'm with STMicrolectronics.
So quick agenda, what we want to look into. So first of all, quick introduction. What is our motivation to look into TLM protocols or standardization? I will show you a few examples of serial protocols we are looking into. Then we will share some thoughts on TLM standardization. And then we will show you some serial protocol scenarios. So these are really real-world scenarios we look into and we want to address with our solution. And so we will relate this with existing standards, and then we will have a quick outlook regarding this activity, what we want to achieve, what are the next steps. First of all, I should do a quick introduction what we are doing. Bosch, you may know all the household goods, appliances we are doing and so on, but Bosch is also active in the automotive business, and typically what we have there, we call them electronic control units, ECUs. So these are little small embedded computers. They sit in your car. They do some sort of controlling. Some sort of controlling means like, probably your combustion engine. What do we have to control? Control would be like injection, ignition, and so on. Typically, these ECUs are assembled of a microcontroller. And on top, these microcontrollers are surrounded by a lot of ASICs. And typically, in our case, we hook up these ASICs using serial interfaces. That's one use case. We do have bigger systems. These are the printed circuit boards, so to say. So it's not like an SoC, it's a little bit a bigger system. Also, of course, we can network these ECUs. Like we have a bunch of these ECUs. They're communicating. They're using a controller area network, FlexRay, just to name a few. So now I'm in the research department, and our job is to stitch together these virtual prototypes based on IP. And guess what? We are not developing all the IP blocks on our own, so we rely on third parties, suppliers, and so on, and we have to integrate them. The problem we face is now that the serial interfaces, they're not very well standardized. So what we have to do is like we start to write some adapters, transactors, we have to validate it, things do not work, we have to debug it, so we spend a huge effort. So the motivation here is that we want to have a seamless approach so that we can stitch together IP and we don't have to spend this effort. So that's the motivation to look into standardizing other protocols other than, for example, memory mapped buses. And of course, so we stitch together these virtual prototypes for our business units like DGS, Diesel Gasoline Division, to develop software early in the design flow efficiently. Here are a bunch of serial protocols we are currently looking into with regards to this effort. So I won't go in depth into all of these protocols, just to see the variety, and actually they cover kind of different varieties. It's pretty good. So we have the protocols, the controller area network, probably you've heard about it, which is used to connect several of these control units. And then the other two, I2C and serial peripheral bus, these are the interfaces used to connect these little ASICs connected to a microcontroller. So the upper one, we would say this is inter-ECU, and the other two are like within the ECU, you connect things. So and now you see they really have different flavors. So some protocols are really well standardized. CAN, for example, the frame, how it looks like of this serial protocol, the bits that are shifted out is very well standardized. You have this ID, you have the load itself, the data, and so on. Others are not. SPI, for example, there's no standard. People are really doing fancy stuff with SPI. They interpret the bits that come out like how they want. Other things is they differ with regards to their topology. CAN, again, is very well defined. I mean, all the nodes sit on a single wire. They all talk. Everybody can be the master. They fight for the bus. There's arbitration. With the serial peripheral interface, for example, the user can come up with different topologies, broadcasting, daisy chaining, point-to-point connections. So they have all kind of different flavors. So when you design now a TLM standard, there are two extremes probably. You can say, well, I come up with something very generic. You say, well, I have a very generic payload, probably have a serial clock in there, and then I have a pointer. I'm pointing to this data frame. Everything is fine, everything is covered. So benefit, simple to design. I mean, simple payload, not much coding has to be done and so on. The drawback is that actually you often oversee corner cases or actual features of protocol. You say, it's working for CAN, it should work for SPI. And you really oversee that you have different modeling needs for different protocols. So in the end, if you have a very generic framework, easy to design, but you probably then have very complicated rules, and you have limits with regards to their use. Then the other thing is you can be very specific. Very specific means you really nail it down. You say, that's how it looks like, my payload looks exactly like this. So difficult to design, you add more and more details. It's also, we are trying to standardize this. It's kind of difficult to agree upon because you have all these stakeholders and everybody saying, I want to model it like this. Nah, I want to model it like that. So that's the drawback of this approach. Another drawback is you may re-implement things. For example, I2C and CAN, they both need an arbitration. Do you implement it for both separately? You don't share code? That's a drawback. Nevertheless, there's also the benefit that you ensure or enforce interoperability. You really nail down the payload. There are no extensions, nothing. You have to follow this. So you stitch things together, it should work. So the message here is you have these two extremes, but probably you should find something in the middle, a good compromise. So good properties of a TLM standard. You look for very straightforward protocol rules, easy to understand and to comply with. Powerful. Of course, you want to capture all the relevant features of a protocol. Not you say, oh, sorry, it's an ad hoc solution. We don't cover this. And so you also have very well-defined corner cases. Flexible, you don't want to enforce modeling objects, like you say, oh, now for monitoring, you need this vendor-specific thing. And you also do not want to have limits. For example, you say, oh, we have this deeply nested design hierarchy, and, oh, sorry, our socket doesn't support this. So the approach we took is the following. So initially we talked to some of our suppliers. Here are the ones we are allowed to name. So ASTC is an Australian company doing system-level tools and also consulting, Infineon, STMicrolectronics, Synopsys, and us. So, and then we started to identify these real-world scenarios. I will show a few of them later on. And we talked every 2 weeks, and we came up with a kind of document listing all these scenarios we want to cover with our solution. The other thing we did is we set up a GitHub repository, we shared code, and that was really great because we could look at each other's code and we could say, hey, these are the pros and cons of this implementation option. And we had really a good discussion basis, and we also could exchange and understand the other implementation. Was really helpful. Now the next step, we are not done here, so we have some different approaches. We want to converge on a single modeling base, and once we are done, we want to donate this to Accellera. So that's the plan so far. So just a few scenarios. So the first one, we start with CAN, Controller Area Network, which is used to communicate between electronic control units. And remember, this is a bus, broadcast bus. All the nodes sit on a wire. Everybody can talk. Everybody's listening. So the CAN frame typically has an ID field, followed by, for example, the real payload. And the thing is, they can all send simultaneously. And the whole wire, I make it short, it's wired NAND behavior. So in short, the guy who's sending a 1 first is losing the arbitration. So and now the scenarios we figured out is, for example, a reset. So what's happening on the real hardware if you are doing a reset? So like you have these two ECUs, they are talking to each other. It's not like on an SoC, you have a reset line, so they don't know what's going on. So the ECU A does not know what's going on in ECU B, for example. So, and then we found two scenarios. For example, let's assume two nodes are sending, they're fighting for the arbitration, and then suddenly the guy who would actually win is going to be reset during he's fighting for the arbitration. So that would mean, oh, the winning node is changing. So it's one scenario we figured out, and the other scenario, for example, is then you do this reset during transmission. What would happen on the real hardware when you are doing a reset during transmission? Suddenly the node that did win actually stops sending, and all the other nodes are listening, and they're expecting certain bit patterns. And then they say, hey, wait a minute, this bit pattern is missing, like a CRC sum or bit stuffing, whatever's all this in. There's an error, right? So now the question is, how do you do this in TLM? Do I really model all these phases? Yeah, I probably need these phases if I want to accurately model this reset behavior. And so currently what we do is how it is implemented. Yes, we do model these phases, so we know exactly when arbitration stops at which time, when the transmission starts. And for example, to support a reset, we do have a cancel in the interface. So it means we can withdraw a transaction that is already sitting on the wire, let's phrase it this way. Another thing is the broadcast of an SPI. So SPI, probably a quick recap, it's a full duplex synchronous interface. So you have in both directions going data back and forth based on a clock. And usually the struggle we have is, So this is our main interface. We hook up these ASICs. And the microcontrollers, they never have enough chip select lines. So there's also a chip select line. So what happens is we were connecting multiple of these slaves to a single chip select line. And then guess what? Both are selected. Data is shifted into this device, and both want to answer, and you want to prevent this. Usually we do this with a dedicated address field. We say, well, up a few bits, we interpret them as an address. And then slave 1 is saying, oh, that's my address, 0, 0. I'm the only guy who is responding, the other stays silent. So that was one scenario, and we tried to implement this in TLM as well. And then the outcome was, well, the slave should not block, because, for example, all slaves should get the start of the frame simultaneously, because this also marks the beginning of the frame. I think this is my last scenario. RTL simulation, that's also a big topic for us. So first of all, we are doing chip design. So we want to be capable of doing HDL co-simulation. And another thing is also we have a lot of legacy code within Bosch, and usually we can easily translate this into SystemC. We can integrate it, we can have a single kernel simulation. So we definitely want to support RTL co-simulation. And then the problem here was in a simple setup. So you have this TLM master. It's hooked up to this adapter doing a transactor, TLM to RTL, and here you really have this RTL-ish slave sitting there. So remember, it's a duplex protocol, so we are sending frames to the adapter. That's easy. In TLM, we have all the frame data at the very beginning of the frame. Great. So this transactor can immediately say, okay, now I start to slowly shift out my bits as on the real world. And then the backward pass is kind of the tricky thing, because this guy also starts right away. It's RTL. It doesn't wait. It's being clocked. It's shifting out the return data right away. And the transactor now has to provide some transactions back to the TLM domain. What is it? And well, but it doesn't have all the data yet, right? Because it's shifted slowly out of this device. So for the transactor, it takes him some time to assemble a complete transaction. So do you wait now till you have all data available? But probably that, hey, we want to have a start of frame transaction here, kind of marking the beginning of a frame. And then here, how we did it, we allow an update phase. So we say, okay, this guy gets the first bit, he can send over a transaction, but then he's also allowed to issue updates on the fly. And I think that was my last scenario, and I switch over to Jérôme.
So let's continue with SPI. So another fancy things Martin mentioned initially with SPI is the spatial topologies sometimes. So one of these topologies is the daisy chain, where slaves are connected together in this fashion. So basically you have to support this when doing the SPI standard. And one of the things we found with our experiments was the fact that in this setup, so you've got shift registers inside the slave IPs of various lengths. There's nothing that will tell you that all the slaves have the same shift register length. And in addition, nothing tells you that the master will send the exact amount of bits that is needed to fill the shift register. So you need to accommodate the fact that you may receive in the slave more bits or not enough bits to fill your register, and then you have to shift it out to the other slaves. So the outcome of this experiment was that we need in the TLM standard some data container that will help writing these models so that they are able to accept whatever number of bits they will receive. Now we are shifting to I2C. I will not talk much about I2C, but just to highlight one thing, which is we found, as potentially many of you knows, I2C is sometimes implemented with hardware controllers, but there is also the possibility that it is implemented completely in software by driving directly GPIOs, because the protocol is simple enough. So that's what we call software emulation technique. And this means that basically if you want to connect one guy that is using software emulation and the other guy that is using a real hardware controller, basically you are in the same situation as RTL co-simulation, because you have to really take into account RTL-like level of granularity. Which means that we need to be very careful about how arbitration is modeled and, well, how things are properly synchronized between the TLM world with the hardware controller and the TLM world, which looks like the RTL world actually. And what we discovered as well is that, okay, we say we are mainly, at least Martin is coming from the automotive domain, I'm doing also some automotive-related virtual platforms, but we are standardizing SPI and I2C, and this usage of this protocol is not limited to automotive, actually. For instance, related to the previous slides, you could say in automotive we don't use software emulation, so I don't care about synchronizing these things. Yeah, but maybe if you want to do virtual prototyping for other domains, like Internet of Things, for instance, you will get microcontrollers that are very cheap, that don't have a built-in hardware controller, and that's using software emulation, for instance. Also, we are seeing now a trend that customers in that domain of Internet of Things, they want to validate the global system in the same way as Bosch wants to validate automotive systems, which means multiple microcontrollers with sensors and everything. So we've got exactly the same need, and we need to be able to virtual prototype everything before having the real system. So just to say that the outcome of all of this is that we really need to address and to think about all the domains into these protocols will be used, and not to just sit on some features that looks like the cheap feature that will never get used. Now, we are building a TLM standard. So what is the relation with what is existing? We've got good job has been done in the past with TLM1, for instance, and TLM2. So TLM1 was a very generic standard, which is part of IEEE 1666. So, which provides often a good basis to build new protocols. But what we found is that many interfaces there were, but not everyone was covering our needs. So we needed to design new interfaces. TLM2, which was designed for memory map bus protocols with some extensibility possible, of course. So what we found is that if you use, that's the generic part we were mentioning initially in the first slides. If you take something that is too generic, then you will end up writing many rules to be able to constrain that generic framework to actually fit your need. And the problem is that, will everyone follow these rules when you will receive an IP? No one knows. Also, there are some technical problems like AC export limitation. We can talk again later on if you want, which is limited hierarchy support. So in the end, TLM2 is a good standard for memory map buses, but we will not use it probably as a basis for our efforts. So what should we use then? And what are our guidelines? Well, first, use ST-port. That's a question of limitation regarding hierarchy. And then what is the other important thing we want to highlight is the fact that you need actually two sides to this standard. One side is talking to the model-to-model interfaces. So you need to have something that is very simple, very straightforward, with a limited number of rules needed to actually constrain. And this is the interface between the models. And then you need to talk also to the guy that will write the IP model. And this is what we call the convenience layer. Next steps, we want to address other protocols that are required in the automotive domain, such as Ethernet or FlexRay. And we want to donate something that is final to Accellera as a basis for a new standard. And we want you to be involved, because we need some feedback to say, hey, how this set of scenario relevant? Are we missing something? Do you have a fancy use case for SPI that we missed, for instance? So that's also the advantage of participating in these Accellera events and Accellera context, is that we can talk to each other. And so what we hope in the end is that we will end up with a virtual plug fest where we will demonstrate that multiple vendors are able to plug their microcontrollers or ASICs together so that we can prototype the whole system.